The year is 1945. After an all-night alcoholic rager, the inebriated sci-fi author Murray Leinster wrote of a futuristic machine which could bring hand drawings to life with nothing more than a metal arm and melted plastic. Little did he know, his ideas, which were witchcraft at the time, would become a reality in the next 50 years. The 80s were truly a decade punctuated with firsts. The first cell phone from Motorola, the first version of Microsoft Windows, the first Nintendo Game Boy. It was an era where technology was revolutionizing life, culture, and business to the point that Time named the computer Man of the Year in 1982. Amidst this technological boom, perhaps forgotten was the transformation of manufacturing techniques. Budding inventors and entrepreneurs quickly realized that traditional manufacturing methods involving searing metal shrapnel needed to change. Enter rapid prototyping, aka additive manufacturing, aka 3D printing. In 1984, Charles Chuck Hall filed a patent for the first commercially viable additive manufacturing method dubbed stereolithography, or SLA. His actions started a chain of events across the country which would lead to the patent filings for two additional manufacturing methods in 1988: fused deposition modeling, or FDM, and selective laser sintering, or SLS. Three techniques developed over 3 decades completely revolutionized the way that industries approached manufacturing their products.
Much later.
Today, rocket engines are manufactured using SLS, and SLA is prevalent in medical and surgical applications where precision is paramount. FDM, however, grew into the poster child of modern 3D printing, with hobbyists utilizing the tech in DIY projects and industries adopting FDM as a way to not only quickly prototype preliminary designs, but also to manufacture complex composites for the harshest environments. And with that said, let's discuss the inner workings of FDM printing. In order to understand FDM, we need to discuss three components: the software, the material, and the machine. So let's start with the software. The majority of FDM 3D printing projects follow the same basic workflow, from design conception within a CAD software to the common .stl file format to a slicing software, which allows the printing machine to build up a layer-by-layer design. CAD, or computer-aided design, is a tool to build 2D and 3D models in a digital environment before manufacturing is needed. And while we will not discuss the intricacies of CAD softwares in this video, it is important to note that the vast majority of 3D prints are conceived in this stage. From here, the 3D model is converted to the .stl, or standard triangle language file format. This is a file type which uses the geometric details of the 3D model and stores them in high detail using a triangular mesh. From the STL format, we can start working in the slicing software. Between the different 3D printer manufacturers, slicing softwares can vary quite a bit. However, the base functionality remains the same. Slicing softwares will take 3D models and, as the name implies, slice them into thousands of layers, which the printer can slowly build up. Now let's move on to the next major component of 3D printing, the material. Filaments are essentially various plastic polymers which get fed through the printing machine to build up models. They are classified specifically as thermoplastics, which makes them unique to your common household plastic in the way that when you heat up common plastic, it will burn, releasing toxic fumes and pollutants. Thermoplastics, however, will melt when heated, allowing them to be shaped into usable geometry before they cool and solidify. On the market, filaments can commonly be purchased in the weights of up to 3 kilogram spools and in diameters of 1.75 or 2.85 millimeters. Today, the most common types of filaments for recreational FDM printing are ABS or PLA. These filaments have garnered massive popularity due to the fact that they are inexpensive, non-toxic, and relatively durable. While ABS and PLA have dominated the recreational market, there are hundreds of niche filaments available for every type of project, from rubber-like flexible filaments for soft touch products to carbon fiber composite filaments, which are used in engineering-grade products. Now, let's talk about the star of the show, the machine itself. FDM printers are composed of the same basic components: the base, the build plate, the movement tracks, and the extruder. First, we have the base, which provides support for the rest of the structure and typically contains the control panel and the input-output ports for the printer. The build plate sits on top of the base and is where the parts are constructed. Between different brands of printers, the build plate can vary greatly in size to allow for larger or smaller size models to be created. Many modern machines also utilize a heated build plate, which improves the first layer of a 3D print and improves the overall part quality. The movement tracks carry the nozzle around the build plate in the X, Y, and Z direction. These are another component which varies significantly between printer brands. Every company has a unique method for moving the nozzle around, whether that be servos, gear systems, or linear actuators. Finally, let's talk about the extruder. Arguably the most important component of the machine, the extruder is the key signifier of quality. Oftentimes, the only significant difference between a $4,000 machine and a $400 machine will be the quality and the capabilities of the extruder. Typical extruders contain a gear system, a heat sink with one or more cooling fans, a heating unit, and a nozzle. The gear system on the extruder pushes filament through a channel into a superheated nozzle. The heat from the nozzle will then melt the filament and allow it to flow out the tip of the nozzle like ink from a pen. The heating capabilities of the extruder are paramount to the performance of the 3D printer. The nozzle temperature needs to be highly calibrated and consistently monitored. Too cold, and the filament will not melt on contact and clog up inside the nozzle. Too hot, and the filament will flow like liquid out of the nozzle and ruin the final model. The excess heat generated by the unit is then vented out via a cooling system. And there you have it. With input from the slicing software and filament as material, the 3D printer is able to turn a digital design into a physical model within hours. Thank you for joining me on this episode of 3D Printers for Dummies. I'll see you in the next one. Shaktiman out.